Good morning, everyone.
Good morning.
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 Good morning.
Good morning. Ooh, Christmas trees.
Good morning.
We have a quiz today after class, right?
Yeah, we always have a quiz. So we have already finished chapter 7 last time. We're in, if we're going to recall what we have in chapter 7, we discussed about quantum numbers. So we have N, L, M sub L, and M sub S. So N is your principal quantum number when it is any positive number. It describes the size. And then L has something to do with the shape. And the value of L depends on N. So the value of L would be from N minus 1, or we could say from 0 to N minus 1. And whatever is the number that we have, we assign a letter to it, like 0 is S, 1 is P, 2 is D, 3 is F. So it has something to do with the shape. Now, M sub L, on the other hand, has something to do with the spatial orientation. And its value would be from negative L to positive L, including 0. Okay, so what the M sub L tells us is the number of orbitals that you have. So if this is the shell, this is a subshell. So this is usually the number of orbitals in a given subshell. Okay, and the last one that we have from last time is the spin quantum number. So its value is either positive 1/2 to negative 1/2. So it just tells us that in an orbital, the electrons that you can have must have opposite spin in occupying it. And based on the Pauli's exclusion principle, okay, an orbital can accommodate at most 2 electrons. Okay, so if I'm not mistaken, we end up with electron configuration wherein we follow the Bow principle that tells us that electrons, okay, will fill up orbitals according to the energy level. So how do we decide the energy level? We have the N plus L. So what is the N plus L? Whatever is the principal quantum number added with the azimuthal quantum number, it will give you a number that will ask, okay, the energy level of a given orbital. And we end up with this sequence, or the one that we have here, or by the end of the semester, like the Christmas tree that we have here. Okay, or as I mentioned, you can just look at the periodic table and you can assign the orbitals to the region in the periodic table. So the S is the first 2 groups there, the P is the last 6 group, the D is the transition element, and the F is the inner transition element. And the number that you have here, the principal quantum number, has something to do with the period. The only one where the period will be modified is when you are introduced to the D, where it starts at 4, because the rule that you have is whatever is the period, you subtract it with 1. Now for the one that has an F, it starts with the 6, so you subtract it with 2, okay, and then you will get there the number that you have. Okay, so we're going to continue writing the electron configuration today, and then later on we might start with the periodic table. So they said in this build up thing, there's always an exception to the rule. So for instance, okay, if you're dealing with chromium and copper, so the way that you're going to do here, instead of having the last sequences as 4s2 to 3d4, they found out, okay, that chromium would assume this configuration. So if we're going to look at in terms of the arrow, so instead of having it like this, what happened is they see that one of the electron here that should be filled up first is half distributed among the d orbitals. Okay, so that is what's happening here. So you have here a 4s1 instead of a 4s2 and a 3d5. So the same thing that happened with the copper. So instead of having it like this one, so what happened? This electron goes there and they become half filled. So I'm just going to make it clear here. So even though the 4s should be the one that is filled up first, what happened? The d orbital is filled up compared to the s orbital. Okay. So as it says there, in each case, the difference is in the 3d orbital and the 4s orbital. Because if you follow the sequence, you have to fill the 4s before you go with the 3d. But they found out that is an exception to the rule, at least for copper and chromium. So they want, copper wants it to be half filled with the d orbitals, chromium wants it to be filled up with the d orbitals, okay, leaving the s orbital half filled. Okay. So how are we going to do this electron configuration? So the next slide that we have here, we're just going to write electron configuration, the long way and some of the shortcuts that we can do. So for instance, if we are asked to write for the bromine, okay, so what's the first thing that we're going to do? If you are asked to write the electron configuration for the bromine, so the first thing for you to do is determine what's the atomic number. What's the atomic number of bromine? Anyone?
35.
Okay, so you have the 35. So by knowing the atomic number, we will have an idea how many electrons do we have. So if we have an atomic number of 35, how many electrons do we have for bromine?
35.
You also
35.
have 35. Okay, now why do you need to know that number, what we call 35 electrons? Why do we need to know the number of 35? Because that's the amount, or that's the number of electrons that we need to distribute in the orbitals. So the rule that we have, an S would occupy at most 2, a P would occupy at most 6, a D would occupy at most 10, and an F, if ever it's included, would occupy at most 14. Now you may ask, where does we get this number? Okay, we get it from our previous discussion that each orbital occupies 2 electrons. So S would have 1 orbital, P would have 3 orbitals, D would have 5 orbitals, and F would have 7 orbitals. So multiply each of the orbitals by 2, you have the number of the electrons. So in doing that, okay, so you follow the sequence. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So you already how many electrons that's accounted for? 2, 2, 6, 10, 12, 18, 20. Okay, and then 3d10, so that's 30, and then 4p5. Okay, so that's one way. Okay, but there could be an easy way. What is the easy way? Okay, if you have the periodic table with you, the easy way, okay, is to use that periodic table. So I'm going to show you a periodic table. So you have this periodic table here. So what were we going to do? Okay, we find where bromine is. So this is bromine, right? So if you're going to look at the bromine, so the next thing that we could do, okay, where is it? So maybe you can count the rows where it is. So 1, 2, 3, 4. Okay, so that would be what? Something of 4. Okay, so try to do it yourself. I just have to I have to get something.
Professor, you're still muted.
So as you can see, this is the 4. Okay, so this is the S, and this is the P. So what do? You count 1, 2, 3, 4, 5. So in that case, you could see the last orbital that you have there is a 4p5. Okay, so in doing that, just ignoring the one that we have. So that means you said, okay, this is the highest one. So what you're going to do, you just fill up anything below it. So before that, you have 4s2, or maybe before that, you have the 3d10. Okay, so you might ask, where is the 3d10? So if you're going to look at the periodic table, this is the 10 that you have, the one that you have here. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so what is before 4s2? That could be a 3p6, okay, a 3s2, and then a 2p6, a 2s2, or a 1s2. So there's two ways for you to do it. But based on experience, my students find that if they have the periodic table, it's easier for them to locate it. Okay, so they just find the highermost orbital that can be occupied and then walk backward compared to building it up, okay, from the bottom of the orbital going up. Okay, so let's try to go on another one. So let's say we have sodium. So how are we going to what we call look at the electron configuration of sodium? So if we can look at the periodic table using the just the one that I gave you right now. So sodium is here. And if you're going to look, it is in the S. And if you're going to look, the principal quantum number is in the 1, 2, 3, third period. So that means it's 3s1. Okay? So what you're going to do is you walk backward from it. So you could say, okay, 3s1. And then fill up everything below it. So what is before 3s1? You have 2p6. You have 2s2. Okay? And you have 1s. Okay? So you ask yourself, what is the atomic number of sodium? What is the atomic number of sodium? Is it 11?
Yeah, 11.
Okay. So you ask yourself, is this the right one? Is this the electron configuration that we have? So 2 plus 2, that's 4, plus 6, that's 10, plus 1, 11. So that is the complete electron configuration of sodium. Now, the way they do it, you can do it like the boxes. So you might ask yourself, how do we do that boxes? So you want S here. Oops. So I don't want to use this writing font. So you could have it like that one, and then that one. So this is 1S, 2S, 2P, 3S. So you could fill it up here, then this one, and then this. And then you just count the arrow that you have there, you put here. So you end up with this electron configuration. So that is the complete electron configuration, because there's other way to write them. Okay, one way to write them is using the so-called noble gas configuration. So what does it mean? You're going to use a noble gas. So usually this is the complete noble gas configuration. And then what is the outermost configuration? So for instance, all you need to do is just look at the noble gas before the element that you're working for. So if you have bromine here, the previous noble gas is argon. If you have sodium here, the previous noble gas is neon. So instead of writing the whole electron configuration there, you're just going to put what noble gas you have there. Okay, so if we're going to look at this, what will happen for the bromine, you're going to put here argon and then this thing. So what does the argon represent? If you're going to look at the previous step here, so this thing here, that's the electron configuration of your argon. So how do we put this in terms of sodium? So you're going to write it in terms of neon and 3s1. You get that? So this whole thing here, this is the electron configuration of your neon. So you don't need to write them. You just write the argon or the noble gas that it is equivalent. Okay. Now, the way that they do it, in some ways, they also have the so-called pseudo noble gas core. And this includes the noble gas subshells and the filled inner or the D subshell. So for bromine, this is your noble gas core. Okay? Because the next one that you have here, we have the so-called valence configuration. And in valence configuration, you only include the s and the p orbitals. So what does this mean? So this valence configuration, this is the one that usually participate in the reaction. So these are the electrons that can be found in the s and the p orbitals. What do we call the s and the p elements, if you remember, in your chapter 2? Okay, they are your representative element. Okay, so you can write bromine in terms of the valence configuration like this one. Now, how about sodium? How are you going to write it? Anyone? How are you going to write sodium? Hello? Hello?
2p6 3s1.
How do you write the sodium in terms of valence configuration? Hmm? You write it as 3s1. Okay? Why 3s1 only? Because that's the outermost configuration. Okay? So when we say valence electron, that's the outermost electron. So when we say valence configuration, that's the one that has the highest principal quantum number. So if you're going to look at the sodium here, okay, so you only have 1 3 there, the 3s1. So you write it as 3s1. Okay, so usually the sum of the A and the B in the representative element, that's your group number. So for an element in group 5A of the third period, the valence configuration is this. So if it's 6A, so it is 2 and 4, 2 for the S here, S4, S2, and then P to the 4. Okay, so let's try to do this thing. How are we going to write the electron configuration using the building up principle for arsenic? Anyone? How do we start? So if we have the periodic table, what's the atomic number of arsenic?
33.
33. So all we need to do is build up until we reach 33. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So we have how many already here? 20, 3d10. So you have here already 30. So we have that. That's the thing. So question on that?
Nope.
And if you want to check if this is really the right one, so you can look at the periodic table and you expect the arsenic to be 1, 2, 3, and then the fourth one, 1, 2, 3, 4. So 1, 2, 3. That's one. That's a wonder. So you always use the what we call the periodic table. Yeah. So if you're going to add everything there, okay, that should be the total number of your electron. So you build up the sequence. So you have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So you have already what here? 20. And then you get 3d10, so that makes 30. And you go 4p3. So if you're going to add all of these, that should give you 33. Okay? So there's another one here. So what are the electron configurations and valence electron of arsenic? So we already have arsenic, right? So if we're going to recall arsenic, this is what we have. 2s2, 2p6, 3s2, 3p6, 3d10, 4p3. So the question now is valence configuration. Oh, I think I'm missing something, right? I need a 4s2, a 3d10, and a 4p3. So what would be the valence configuration here?
4s2, 4p3.
I can only look at the one that is the highest there. So I can just put this as 4s2, 4p3. And if I ask what group is arsenic? It is in group what?
5.
5. Because 2 plus 3 there will give me 5. So that's a group 5A. Okay? So the way that you're going to do is it's always the highest unless it's in the transition element. Because the one that we do next is zinc. So what is the atomic number of zinc? Anyone? What's the atomic number of zinc?
30.
Okay, so it's 30. So if we're going to do it, it's just 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. So in that case, you could see that the highest element is in the d orbital. So if you're going to look at the valence configuration, okay, so you have to include the 3d because that's where it is. So you're going to write it like this. You only include the 3d if it's in the d orbital, just like the zinc. Is that clear?
Yeah.
Yes.
So here, let's look at here. So imagine in a world in which the Pauli principle is no more than one electron can occupy an atomic orbital irrespective of its spin. So how many elements would there be in the second row of the periodic table, assuming that nothing else is different about this world? So when n is equals to 2, there are 2 subshells, right? The S and the D. Okay? Now, the assumption that we have here, we know the Pauli principle says 2 electrons in each orbitals. But what if we have a condition like this? Instead of 2, you only have 1 electron per atomic orbital. So how many elements would there be in the second row? If we follow this assumption, no more than 1 electrons. So you have here 1s, no, that's the 2s, and then you have here the 2p. So how many elements do we have there? So if we count it like this, you only have what? 4 elements. This is assuming, look, there's 1 electron. That you know, Pauli principle has what? Anyone?
2.
2. And you could see that in the second period, there's always 8 electrons. You have there the 2s and the 2p, which is 2, and this one at the most 6. But in this concept check that we have, it's just trying to understand if you really dig into the concept. So what if the Pauli's principle, instead of 2, it has 1. So this is how they look like. So that means you can only have 4 elements if you have that condition. Okay? Now, there's still another principle that you need to know. Hund's rule. So in 1927, Friedrich Hund discovered by experiments a rule for determining the lowest energy configuration of electrons in the orbitals of a subshell. So Hund's rule states that the lowest energy arrangement of electron in a subshell is obtained by putting electrons into separate orbitals of the subshells with the same spin before pairing the electrons. Okay, so what does this mean? So this means if you have these so-called degenerate orbitals, so the degenerate orbitals, usually those orbitals in the same subshells, like p orbitals. You have there 3 degenerate orbitals. D orbitals, you have 5 degenerate orbitals. S orbital, you only have 1 orbital there. So what does it mean? So if you have these degenerate orbitals, what you're going to do is you have to fill them up first into separate orbitals before you pair them up. Okay? So for instance, the example that we have here, nitrogen. So when we fill up the p orbitals, we distribute them first. Okay? Because you could put it this way, right? That the 2p orbitals is how many electrons? 3. Okay, you can put it this way, but Hund's rule won't allow that. Hund's rule says you have to distribute first the electrons among the orbitals. So 1 here, 1 here, and then 1 here. That's what the Hund's rule said. Okay, so for instance, if we have nickel, so nickel has 28. So if we follow Hund's rule, this is how it's going to fill up. So look at the arrow. They usually go up, fill up all the degenerate orbitals, and then they go down. So this is how it looks like. Okay? Because one way for you to do is, oh, what if we just remove it and put it here? So that is wrong. You're going to disobey the Hund's rule. Okay, so those are the last thing that you need to remember about this rule. The Pauli principles, the Aufbau principle, and the what we call Hund's rule. So let's try to answer this following electron configuration or orbital diagrams that are allowed and which are not allowed by the Pauli exclusion principle. And if they are not allowed, you have to explain why. Is this allowed?
No.
No.
You might say that there should be, this one should be filled up 2 first with 2 instead of moving it to 3, right?
Yes.
But this can be allowed if you have an excited state. What is an excited state?
When an electron.
Is it like
An excited state.
when they're like charged up or like moved type?
Okay, so when you have an excited state, some of the electron can go up to a higher, an orbital with a higher energy level. So here, it is allowed if you have an excited state. So that means one of the electrons up.
What makes something an excited an excited state? Jeez. What like is
If it has absorbed energy.
okay?
Okay, so one of the electrons can be excited and go to a much higher energy level of the orbital. How about this one? Is this allowed?
distributed.
Yes or no?
No.
Is this allowed?
I think yes. I think yes.
P doesn't go up to 8.
No, it's not allowed because this one is 8. What's the maximum for P?
6.
The max is 6. So that is not allowed. Okay? How about this one? Is this allowed?
Yeah.
Yes. Yes.
Yes. And you might say, oh, something is missing. What is the one missing?
S.
This one. So that means it's a 4s0. So that means this is allowed because this is an excited state. How about this one? Is this allowed?
No.
No.
Why?
D can only go up to 10.
Okay, very good. This one, let's make it not allowed. You can only have a max of 10 there. How about this one? Is this allowed?
Yes.
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 No. No.
It's no. Why?
The arrows have to
Arrows.
be one going up, one going down.
Okay, they should have opposite spin. Okay, so you have to identify if the electron configuration is possible or not. Now, another thing that you can use, if you know how to write the electron configuration, is you can determine its property. Okay, you can determine its so-called magnetic properties. So what is the magnetic properties? The ability to be magnetized. Okay, so although an electron behaves like a tiny magnet, two electrons that are opposite in spin cancel each other. So only atoms with unpaired electron exhibit magnetic susceptibility. So that means that's the one that has the unpaired electrons. That's the one that has one arrow up or one arrow down. Okay, so what is this property? So whenever you have an unpaired electrons, that means that substance is paramagnetic. So what is paramagnetic? It can be magnetized. It can be attracted by magnetic field. Now, diamagnetic, on the other hand, okay, they are not attracted by magnetic field because it only has paired electron. Okay, so let's go back to some of the items that we have done. Is chromium para or diamagnetic? Hello? Is chromium para or diamagnetic? Anyone?
Diamagnetic.
It's diamagnetic. Yeah.
So what does the para means? You need at least one lone pair there or unpaired electrons. If it's a diamagnetic, all of them are paired. So is chromium para or dia?
Diamagnetic.
Okay, as you could see, it has a 4s1, 3d5. So as you could see here, all of these are unpaired because all of them are like this. So all of them are what we call unpaired electrons. So that's a paramagnetic. So how about copper? Is this para or dia?
Diamagnetic.
Yeah.
There's a 4s1 there. There's an unpaired one. When you say an unpaired, this one, it doesn't have complete octet or orbital. It only has one. So this one is also para. You see there? The 4s1. It's unpaired. Although the D are all paired up. Okay? How about this one? Is this para or dia? Bromine.
Diamagnetic.
Dia.
Okay?
Oh,
So if you're going to put it here, what is this?
but that's
1,
not paired.
2, 3,
Pair.
4, 5. So you still have
One, yeah.
1. So that is still a para. How about sodium? Is this paramagnetic or diamagnetic?
Paramagnetic.
Para.
Okay, so you
Because
have there a
there's-
3s1. So that is also a paramagnetic. So what else? I'm just going to use the sample that we have discussed. Arsenic. Is it para or diamagnetic?
Para.
Para.
Para. Because if you're going to look at this 4p3 there, so that means like this, right? So how are you going to distribute the 3 electrons in the p orbital? You distribute it like that. So all of them are unpaired. So you have a paramagnetic.
I'm confused though. So do we look at the last number? And
No, I mean, you look at all the orbitals that you have. But usually it's the last one that is not filled up. Okay? Now the zinc. Is it para or diamagnetic?
Diamagnetic.
Dia.
Oh, if we follow this, this is a diamagnetic because it doesn't have any unpaired orbitals or electrons. All of the electrons are paired. So that's how you have it right now to distinguish whether you have a paramagnetic or a diamagnetic element. You just look for the presence of unpaired electron. Okay? So question. So nitrogen, before we go to the next topic in this chapter, is it para or dia?
Para.
Nitrogen. Huh?
Para.
Para.
It's para because as you could see here, it has 3 unpaired electrons. Okay? How about nickel? Is this para or dia?
Para.
Para.
Okay, so you have the 2 unpaired. 1, 2. So this is also a paramagnetic. Okay? So the next topic that we have is how did we end up with the present periodic table? So you learn how the organization of the periodic table can be explained by the periodicity of the ground state configurations of the elements. Now we will look at the various aspects of this periodicity of the elements. So before we go to how Mendeleev do this periodic table, maybe we can look at the history that we have. So we start with Johann Dover-Reiner. So he discussed about this so-called triad. Okay, so if you're going to look at the triad, there are some elements before that has the same properties. If they group them, they have a group of 3. That's why Johann Dover-Reiner called them the triad. And what he observed, the average of the highest and the lowest atomic mass is the same as the middle element. Okay. And then John Newlands arranged element, and he found out that when he arranged the element according to atomic mass, okay, the 8 elements repeated its property with the first element. So he called it the law of octaves. So what is the law of octaves? The song Do, Re, Mi, Fa, Sol, La, Ti, Do, right? Have you know the musical notes? Do, Re, Mi, Fa, So, and then it will repeat back to the Do. But the problem with this one is limited until the element calcium. Okay? So what happened? Dmitry Mendeleev and Lothar Meyer, so those are the one, the M and M, that work on this thing. Because they independently propose a periodic table based on the periodic recurrence of properties. Okay? So Mendeleev's periodic table generally organized elements by increasing atomic mass and with similar properties in columns. And in some places, there were missing elements whose properties he predicted. So this is the reason why he got the credit. Okay? Mayer just arranged them. But Mendeleev, when he arranged them, he found out that there might be some elements that exist but not yet discovered with these properties. Okay? And he predicted those properties. So what are those what we call thing that we have? So we have gallium, scandium, germanium. And the term that they have for them is eka-aluminum, eka-boron, and eka-silicon. So he predicted the properties of this eka-aluminum, eka-boron, and eka-silicon. And when these gallium, scandium, and germanium were discovered, it is its properties is close to the one predicted by Dmitry Mendeleev. So that's the reason why he was given the credit for the periodic table. But the arrangement that we have there is periodic properties. Okay, so if you're going to look at the periodic table from this, and then you move back there, and then the properties that you have there is similar to the one in the group. So that is the periodic properties. That's where the periodic table is based on. And they call it the periodic law. It states that when the elements are arranged by atomic number, their physical and chemical properties vary periodically. Just like us, right? We have what we call, is that seasons that we call here in the US? Just like the song is that what do you call it? Winter, spring, summer, or fall. So we are now what? We're fall now, right? Okay. So the same thing with the one that we have here. Now, what we're going to do with this periodic law is we're going to look at some of the properties, okay, like atomic radius and ionization energy in detail, okay, and we try to look at the trends. We also include electron affinity, but there are some anomalies in this compared to the properties of atomic radius and ionization energy. So that's the one that we're going to discuss for the rest of the chapter. Okay? So atomic radius. How do we define atomic radius? So while an atom does not have a definite size, we can define it in terms of covalent radii, the radius in covalent atoms. Okay? So the way that they look at this covalent radii, this is just 1/2 the distance between the nucleus, between two nuclei in two adjacent atoms. So maybe the way that they look at this is like this. So what they do is 1/2. So if you have the distance between that, so you get the 1/2 there. Okay, so that's the radius. But if you're going to look at it technically, it's just the distance between the outermost electron from the nucleus. Okay, so let's look at the trend, and then we'll discuss what are the factors that affect this trend in the atomic radius. So it says here, within each group, okay, the atomic radius increases with the period number. How do we simplify this? What is T to B? From top to bottom, atomic radius increases. Okay? And one explanation for this is you have what? Higher N. So you expect the 2s to be greater than the 1s. You expect the 3s to be greater than the 2s. So that's what it means. Top to bottom, there is an increase in the atomic radius because you're introducing there a new n. So the higher the n, the bigger is the atomic radius, or the bigger is the atom. Now, how about within each period? So that is what? Left to right. So it says here, the atomic radius tends to decrease with increasing atomic number. So what does this mean? Left to right. Atomic radius decreases. So what does it mean by atomic number? Why do you think the radius decreases from left to right? What happens if the atomic number increases? Anyone? What do you have in the atom?
More protons,
More proton. And in addition to proton, what do you have?
more positivity. So
No, in addition to proton, what do you have? If you're
More
going to look at the atom, what are the subatomic particles you have there? So you have more proton, and at the same time, you have more electrons.
Electron.
Okay? More positive, more negative. What does it mean?
they attract.
More attraction. And if there's more attraction, that means your atomic radius within a period decreases. Does it make sense? So all of them, let's say, has the same.
Yeah,
Let's
that
say
makes
2. So if I'm going to look at 2, so we have it like this, right? So if we compare 2s2, 2p3 versus 2s2 and 2p5, which is smaller? Which is smaller between the two? So this is in group 5 and this is in group 7. So which is smaller, the one in group 7 or the one in group 5?
Group 7.
Okay, the one that's smaller is group 7. Why? You have 7, okay, outermost electron there that will interact with 7 proton compared to the one that's 5.
I have a
So
question.
that's
Did you
fraction.
say that the size decreases or increases from
It decreases. Look,
on
here,
top? No, the last one, top to bottom.
top to bottom increases, but this is left to right. Okay, this is within the period. The one that we have before is within a group. So that is another what we call thing compared to this one. Okay, so the main reason why there's a decrease is the nuclear charge. So if the nuclear charge increases, you also increase your number of electrons. Positive, negative, higher positive, higher negative, there's more attraction, leading to a decrease in the atomic size. Okay? Now, what other things that affect the size? So, top to bottom, one of the effect is the quantum number. So, as you could see there, there's what we call a successive shell, which is larger than the previous shell. But here, it has something to do with the nuclear charge. Now, there's still another one, the so-called effective nuclear charge. And if you're going to look at this effective nuclear charge, okay, this is the positive charge that an electron experiences from the nucleus. It is equal to the nuclear charge, but is reduced by shielding or screening. So usually we symbolize it as like this. What is C equals to, if you remember? C is what? Anyone? C is equals to the atomic number, if you remember, right? So if you have CF here, that is your effective nuclear charge. And if you're going to look at the CF, it's just equals to C minus this. And this is your shielding constant. Now you may ask, what does this shielding constant means? Okay. So what happened? Let's say this is your nucleus. You have what? You have electrons here, and then you have what we call the outermost electron. How do you think the outermost electron interact with the nucleus? Anyone?
It avoids it.
Is it easier for it to interact or harder?
Harder.
Harder, because what happened? Your inner electrons will what? Shield the outermost electron from the nucleus. So that's what the shielding constant means. Okay? So the bigger the atom, okay, we could say the greater is the effect of the shielding constant. Why? Because the bigger the atom, the more likely you're going to be shielded by the inner electrons. Just like imagine yourself, you're trying to view, okay, an event, but you are far from the event. So what happens? The people closer to events shield your view from the event. So what happened to you? Are you still interested to look, to view at the thing or to look at the event? Because some of the people closer to the event are shielding your view. Okay, so that's what it means by the shielding constant. And if you're going to look upon this, what we've called effective nuclear charge, so usually it increases across a period. Why is it increases across a period? What's the effect that you have here?
Atomic radius increases.
So why does this increases across a period? Which one increase here? Is it
Atomic
the C
number.
or the shielding constant?
The shielding
Z.
constant.
Across a period. So this is across a period, left to right.
Z.
Z.
C is the one that increases. Okay? So because the shell number is the same across a period, each successive atom experiences a stronger nuclear charge. And as a result, that's the one, another explanation why atomic size decreases across a period. Okay? So in addition to the attraction that you have, the effective nuclear charge can also have an explanation to it. Now, top to bottom, this one is fixed. This is the one that is what we call affected. But this is not as big as the one that you have when C is the one that is increasing. Okay? So if we're going to look at the atomic radius, this is how it is. So you could see here a repeated. So left to right, it decreases, and then top to bottom, it increases, and then decrease again, increase, decrease, increase, decrease, increase. So that's why you have this so-called periodic variation. Okay? And if we're going to look at the representation of atomic radius, this is what we have. So the biggest atom is cesium. The smallest that one we have is helium. So top to bottom here, increases, left to right here decreases. Okay, so let's try to apply this concept in answering this question. So how would you look at the order in increasing atomic radius for these three elements? So bromine, selenium, tellurium. So let's say you have it there. So how are we going to arrange this from the smallest to largest atomic radius?
Smallest is bromine.
So maybe the way that you're going to do is a dual comparison first. Okay, so maybe Se versus bromine, and then Te versus Se. So between Se and bromine, which one is smaller?
Bromine.
Bromine.
So we could say it's like that, right? And between Te and Se, which one is bigger?
Te.
Te.
And then from that, you could say bromine, and then Se, and then Te, right?
Yes.
Yes.
Yeah.
Okay. So that's are the type of questions that you have. Imagine you have 5 elements. You will have a periodic table for this. Okay. So again, atomic size or atomic radius, left to right decreases, top to bottom increases. Because we go now to the next property. And the one that we have here is first ionization energy. So when we're talking about first ionization energy, this is the energy needed to remove an electron. Okay, so we could say this is the amount of energy that is needed to ionize a given element. Okay, so the term there, ionization. Okay, so the energy that is needed to remove an electron. So the minimum energy needed to remove the highest energy, the outermost electron, from a neutral atom in the gaseous phase, thereby forming a positive ion. So we could put it like this. So this is the ionization energy. How much energy you need to remove the electrons. Okay. Now, you can relate the trends of the ionization energy with the atomic radius. So it says here, going down the group, the first ionization energy decreases. So what does it mean? Top to bottom, decrease in ionization energy. So the explanation that you have there, and smaller an atom, the harder it is to remove an electron. So the larger the ionization energy. So top to bottom, what's atomic radius trend? It decreases, right? I mean, top to bottom, the atomic radius increases. So if it's bigger, it's easier to remove an electron. That's why ionization energy decreases from top to bottom. Compare it left to right, right? So left to right, if the atomic size decreases, the ionization energy increases. Why? Smaller molecule means stronger interaction between the electron and the nucleus. And if there's a stronger attraction, that means you have a higher energy. You need higher energy to remove the electron. Okay? Does it make sense?
Yes.
Yeah.
Yes.
So the smaller the atom, the higher the energy that you need. Okay? Because the smaller the atom, the more stable it is. So if it's more stable, that means you need to pump a lot of energy to remove the electron. Okay? So the way that they look at this, ionization energy is proportional to the effective nuclear charge divided by the average distance between the electron and the nucleus. And because the distance between the electron and nucleus is inversely proportional to the effective nuclear charge, ionization energy is inversely proportional to the square of the effective nuclear charge. But you don't need to, all you need to do is left to right, ionization energy increases. And there are some, we could say, deviation on this one, but we just look at the general trend. Okay? Because there's the S and the P, right? Orbital. So they found out that in some of these sequence, there's a little bit anomaly. But if we're going to look at the general trends, top to bottom decreases, left to right increases. Okay, and if you want to see what I mean here, all you need to do is look at this thing. See that thing? So from the S to the P orbital, there's a decrease here. And then once the P orbital is half filled, so if you introduce the fourth electron, remember the P is out, like this one, right? So if you have it like this, if you introduce the fourth one, there's a little bit of a decrease there. And also when you transition from the S going to the P. But if you're going to look at the general here, it's still increasing. So that's the thing that I just want you to remember. Top to bottom, i.e. decreases, left to right, i.e. increases. Look at the trends that you have here. And if you're going to look at the ionization energy, this is what you have. So the one that is the highest is the smallest atom, and the one that is the lowest ionization energy is the biggest atom. Okay? Now, what if you're going to remove more than one electron? Because the first ionization energy is just the outermost electron. What if you're going to remove more than one electron? Okay, what do you expect to the energy that you're going to need? So you can see here, electrons can be successively removed from an atom, and each successive ionization energy increases because the electron is removed from a positive ion of an increasing charge. And there's always a dramatic increase, okay, that occur when the first electron from the noble gas core is removed. So for instance, look at this. Look at the value that you have there, lithium, and then the first and the second one. So if you're going to look at lithium, what's the electron configuration of lithium? You have it like that. So if you remove the first one, it just becomes 1s2. Now, in removing the second electron, you are now what? What can you say about this? This is similar to helium. So this is a very stable condition. So you don't only need 2 times the energy. This is how many times? More than 10 times. And the reason for that is because you are destroying a stable condition. So you're going to need a lot of energy. That's the reason why there's increase in terms of the ionization energy if you remove the second electron from lithium. So the same thing with beryllium if you remove the third electron that you have. Because as shown here, valence shell electrons are being removed. So right of the line, noble gas core electrons are being removed. So once you go to the noble gas core, you're going to need a lot of energy in removing it. So let's try to apply the same concept that we have with atomic radius with this one. So arrange them in increasing ionization energy. So you can do the dual comparison. To help you guide this thing. So between arsenic and what is SB? Anyone? What's the element SB?
Yeah.
Antimony.
Antimony, right? So between arsenic and antimony, which has the highest ionization energy?
Antimony.
This is antimony, like this one. Try to look at the definition here. Again, this is what? Smaller, or this is bigger than that one in terms of size. So we could say, in terms of ionization energy, arsenic is bigger than that. And this one smaller than arsenic, then you have it like this. So if we're going to look at this, I think this is the sequence that we have. Make sense? So
Yeah.
the thing that you need to remember in the sequencing here, the smaller the atomic size, the bigger the atomic radius. The bigger the atomic size, the smaller is the ionization energy. That's the take-home message that you need to remember here. Now, let's go to the other one, but this is not as straightforward as ionization energy. So the way that they call it is electron affinity. Okay, so they said electron affinity is the energy change for the process of adding an electron to a neutral atom in the gaseous state to form a negative ion. So what does it mean? You have an atom and then there's an electron that is being added and you form an anion. Okay. So electron affinity is a little bit complicated, but you can still put a generalization in terms of the trend. Why is it a little bit complicated? Because you might have a negative and a positive energy change. So a negative energy change, that means an exothermic reaction, a stable anion is formed. So the larger the negative number, the more stable the anion. Small negative energies indicate a less stable anion. You also form a positive energy change, which indicates the anion is unstable. Okay, so if you're going to look at this electron affinity, I think the way I try to ask my student to this one is just look at the trend. Although there's a lot of anomaly here, you still see the general trend. Okay, so the trend is toward more negative electron affinities going from left to right in a given period. So if you're going to look at, these are the things that makes it a little bit complicated. 1A, 3A, and 4A, they form some sort of a stable. And it is really understood because most of them has less number of valence electron. Remember, the one that you're after is the formation of an ion. And the formation of an ion is more favored if you have more valence electron. Okay? Because if you have an ion, that means you receive an electron. So if you have less electrons already in the valence electron, it's impossible for you to receive an electron. Okay? Unlike if you have, let's say, the group 6A and the 7A. So 6A would form what? The -2, an ion. 7A would form the -1. Okay? So it's easier for them to receive an electron. That's why the term that you have, electron affinity. Okay? How are you what we call get along with the electron?
I'm sorry, if it's -2, how come in the p orbital there's only one more?
What do you mean one more?
Like in
What are the group 6A? Usually you have their oxygen, right? When oxygen form into ions, what's the charge that you have? Isn't it O2 minus?
yes.
So that's what I mean by what we call getting electron. Why do you think they form a O2 minus there?
No, I'm
Because
talking about the numbers, like the NS2, NSP4. Like
no, so this is the way that when you put an electron to them, okay? So these are all just +1 electron that you have, that you form there. But you could see the more stable that you have there is if you add 2 electrons. Okay, so this is the group valence, right? So if you add 1 electron to them, this is the one that is formed. But as you could see, the 6A, they usually don't form a -1. They form a -2. That's why I told you group 7A and 6A, the one that usually accept electron. Okay? So if you're going to look at this, this is just how we're going to look at this. Electron affinity. So we could say left to right, electron affinity increases. Okay? Based on this. So the one that has the highest electron affinity are the group 7A. Group 8A, they will not accept any electrons because they are already very stable. Okay? If you're going to look at the value that you have here, this is just messed up. But if you're going to look at this one, look at this here. And I would rather look at this one compared to that number. So we could say EA, left to right, it increases, just like your ionization energy. Top to bottom, if you're going to look at this, the decrease is not really what we call pronounced. You could see here, and even here, look, it increases and then it decreases. So I could just put it in terms of this one. That's why it's a little bit complicated, not as straightforward as atomic size or radius and ionization energy. And the only way that we can relate electron affinity is we just say that the non-metallic properties, I would say, because from left to right, the non-metallic properties increases. And from left to right, the metallic properties decreases. Okay? So if you're going to look at the electron affinity, if you have here, they're already less than 0 because they are already stable. The same thing that you have around here. Okay, less than 0. So that means exothermic. So what do we have so far? Top to bottom, increase in atomic radius, decrease in ionization energy. Left to right, decrease in atomic radius, increase in ionization energy, increase in electron affinity. That's what we can have right now. Now for the metallic properties, where are all the metals? Usually they are in the left side. So left to right, it decreases. And if you look at here, elements with low ionization energy, they tend to be metals. And those with high ionization energy, they tend to be non-metals. Okay? Now, what is this thing with this metallic property? If you look at the oxide, what is oxide? Anything that has an oxygen attached to another element. Okay? So what did they observe? If you have a basic oxide, usually it reacts with acids. And most of the metal oxides are what they call basic. So if it's soluble in water, their solutions become basic. So what are these? Magnesium oxide, sodium oxide. So whenever they react with water, what do you think produce? Making it basic. So when you react with water, okay, what produces? You have a magnesium 2 plus and 2OH minus. The same thing here. That's what makes it basic oxide. Compared to the acidic oxide like CO2, SO2. You react it with water, what happened? What do you produce? An acid? Does it make sense?
Yes.
So when you have an oxygen attached to another non-metal, when you react it with water, usually you produce an acid. So that's an acidic oxide. If you have a metal with an oxygen, you form a basic oxide. Now, if you have an amphoteric oxide, so these are the one that has the semi-metals, that has the acids and the bases. So the rest of the things that I have here is just the different groups. And usually I don't ask question about this one. So the alkali metals that you have, the one that is different here is the hydrogen. The group 2A, the alkaline earth metals. So this one is the most reactive. The alkaline earth metals, the group 2A, and then the group 3A. So this is odd because you have an acidic, amphoteric, and basic oxide. And then you have the group 4A. So if you're going to look at the group 4A, these are the different oxides that they have. And then the group 5A, the 6A, that includes your oxygen and sulfur, the 7A, which are the halogens, and then the noble gases, okay? Whose discoverer celebrated his birthday yesterday together with Niels Bohr, okay? So if we're going to summarize what we have so far here, so maybe this is how we're going to look at it. So the metallic proper character is right to left, it increases. Okay, left to right, the metallic property decreases, or the non-metallic property increases. And if you're going to look in the radius here, electron affinity, first ionization energy, and then electronegativity. Okay, so I think this ends our chapter. And we have 2 more weeks before we're going to have our exam on this one. So what I'm trying to do, next week, we proceed with 9. And then on Tuesday, before the exam week, we're going to have the whole session review from chapter 4, 7, and 8 to prepare you for the exam. Okay, so do you have any question?
Chapter 9 isn't on the exam, correct?
No, chapter 9 is not on the exam, but we're going to proceed on it.
Okay, thank you.
For the
Thank you
class
so much.
recordings, could you post the last 2 sessions?
Yep, I'm going to do
Oh.
that.
And where can we find the ones like the old ones?
The thing is, I think the other, I'll try to what we call put the one that I can, because usually every 2 weeks I lost the recording.
Yeah, because I remember you saying that you were gonna put it on YouTube, but like
Yeah, I have not put the other ones on the YouTube, but it should be up by this weekend.
Okay, thank you.
Okay. So you have a quiz. Again, five items, 5 minutes, multiple choice, open notes. After this one, and then next week, maybe the transition between Tuesday and Thursday, you have the chapter quiz, but I'm just going to include 7 and 8 in one chapter quiz. That's for next week. So this week you finish the blackboard, I mean the owl that you have. Okay. Because I want everything, but when we do the review sessions, it's just like you're taking already the exam on that day. Not just that you're just starting to answer the question, because I don't know if you knew it, if we're going to look at the things that we have here. So if you're going to look at the reviewer, so if you open the exam 2 reviewer solutions there, you could see some short explanation on the answers that I have. I don't know if you're familiar on that. At least this is started in exam 2. Okay. So any question?